Okay, so this is a continuation of the Carnot cycle derivation. So basically what we're trying to prove is that 1 minus QC over Q hot is equal to 1 minus TC over T hot. Okay? For a Carnot power cycle, so this is power cycle. We know any cycle will always operate between a hot and a cold reservoir to create work or power. So the idealized cycle on a TV diagram had basically this shape over here. Where this will be Q hot and this will be Q cold. So we did the derivation, we did some of the derivation for this. What we're trying to achieve is the work, what you put in is this. So we derive the top part, the value for the work to be equal, is in the last page over here, to this expression right here. So where the work is equal to NR T hot log V2 over V1 plus T cold log V4 over V3. Okay, so basically now what we need to do is to find Q sub H. So that's for the section between, so 1, 2, 3, 4, so it's between 1 and 2, and V. Okay, so let's see. Over here, I'm going to do a simple derivation of this, but basically for a cycle, the first law of thermodynamics is what? Q minus W equal to the change in internal energy. This is if we neglect kinetic and potential energy. So you see that when you go through the cycle, the overall change, you start from 1 to you end up at 1. So the overall change will be 0. And basically what I'm trying to say is that the amount of energy that is going between 1 and 2 is really equal to the amount of work between 1 and 2. And this is basically what you will get as well from this equation. So we could say using this that Q sub H should be equal then to work 1, 2. And what is work 1, 2 equal to? So we can go to the previous derivation. Work 1, 2 was equal to P1 V1 log V2 over V1. For an ideal gas, we can do the same thing. This will be equal to what? N R bar T1, which is equal to T hot. Remember? T1 T hot. So at the end, we have Q hot equal to N R bar TH log V2 over V1. Okay, so now we can go and substitute this equation here and this equation here into this equation over here. All right. Okay, so when we do the substitution, what do we get? So we're gonna have on top and R bar T hot log V2 over V1 plus T cold log V4 over V3, and all this divided by n R bar T hot log V2 over V1. Okay, so now you can see right away that this can cancel, and this will actually be equal to what? 1, you divide this one by this one is the same, plus Tc over T hot log V4 over V3 divided by log V2 over V1. So as you can see, we are almost there, but the almost there is probably going to take a couple more pages. So remember, what we need to prove is what? That this is equal to 1 minus Tc over Th. So we are almost there, we have everything, so what needs to happen is this to be equal to minus 1, basically. So now I'm going to switch to a thinner pen because it's going to be a lot of indexes, and it might get too confusing if the marker is too thick. So in order to do that, we need to look at, let me do this figure. So remember, the cycle is equal to this 1, 2, 3, 4. So we're actually going to look at these two over here, at the two polytropic cycles, in order to get the relation for these ratios. So let's say we're going to say here process 2, 3. Process 2, 3, what do we know? We know P2 V2 to the K will be equal to P3 V3 to the K. Okay? So from here we can write down, let's say P3 over P2. P3 over P2 will be equal to V2 over V3 to the K. And let's call that expression A. Now we also know that we are dealing with an ideal gas or an ideal substance, so in that case we can write down P2 V2 equal to N R bar T2, P3 V3 equal to N R bar T3. So from these two equations we can get what? P3 V3 divided by P2 V2 will be equal to T3 over T2, or we can get the relation P3 over P2 will be equal to V2 over V3, T3 over T2. Okay? And what is T3? T3 will be equal to T cold, and T2 will be equal to T hot. So really what we have over here is P3 over P2 equal to V2 over V3 T cold over T hot. So now if we equate A and B, by the way, this is not new. If you go back to the previous video, this is what I call the polytropic relations, okay, for an ideal gas. So over here we're going to have P3 over P2 will be equal to what? V2 over V3 to the K will be equal to V2 over V3 times T cold over T hot. So if I just look at this side of the equation, all right, I'll go to the next page. So let me just rewrite it. We will have V2 over V3 to the K equals to V2 over V3 times T cold over T hot. So over here I can rewrite that, let's say T cold over T hot will be equal to V2 over V3 K times V2 over V3 to the minus 1. So this, when it goes, if this goes to the other side, will be V3 over V2, which is the same as this. So at the end we have that Tc over Th will be equal to V2 over V3 K minus 1. Okay, now we do exactly the same thing for the process 4.1. So remember 4.1 is this one over here. So exactly the same thing. So we'll have P1 V1 to the K will be equal to P4 V4 to the K. So here, I don't know which one would be better. Let's say we do P4 over P1 would be equal to P1 over V4 to the K. And this would be our relation C. Now, assuming both of them an ideal gas, we're going to have P1 V1 equal to N R bar T1, P4 V4 equal to N R T4. Maybe here I'll do the transformation now to save a little bit of time. T1 will be equal to T hot, T4 will be equal to T cold. So basically from here we can get that P4 over P1 will be equal to what? V1 over V4 times T cold over T hot. We equate the two relations. And what do we get? P4 over P1 equal to V1 over V4 to the K equals to V1 over V4 Tc over T hot. So basically here you can see the idea is to equate this Tc to this Tc. So from here we can get Tc over Th, and let's try to get the same denominator K minus 1 over there. So Tc minus Th will be equal to what? Will be equal to V1 over V4 to the K times what? V1 over V4 to the minus 1. So we get that Tc over T hot equals to V1 over V4 K minus 1. Alright, we're almost there. So now we're going to equate this relation to this relation over here. Okay? So next we have Tc, so T cold over T hot will be equal to V2 over V3 to the K minus 1 equal to V1 over V4 over the K minus 1. So again, if we only look at this side, we can say that V2 over V3 should be equal to V1 over V4. Okay, so now is when we need to go to the initial page of this one. And what are the two ratios we were interested? V4 over V3 and V2 over V1. Okay, for this equation. So now from that one, we can say, or V2 over V1 is equal to what? V3 over V4. Alright, so recalling, the equation that we had over here, the efficiency equals to 1 plus Tc over T hot log V4 over V3 divided by log V2 over V1. Okay, so this should be equal to what? 1 plus Tc over T hot. So if you want, we can replace the log V2 over V1. So we'll keep the top one as it is, log V4 over V3 divided by log. So V2 V1 could become V3 V4. Okay, and now this is just simple algebra. 1 plus Tc over Th, and this will be equal to what? Log V4 minus log V3 divided by log V3 minus log V4. So really here doesn't matter really what happens, but in the real case what happened? V3 should be open than V4, but even if it was the other way around it would work, because this term will be, in this case this one will be positive and this one will be negative. So no matter what, all this term here will basically be equal to minus 1. So at the end we have what we wanted to prove is that the efficiency will be equal to 1 minus T cold over T hot. Okay, so we did all this derivation, but really what's important over here to remember, just for the power cycle, is that the general definition was 1 minus Q cold over Q hot. But for a Carnot cycle, which is kind of ideal cycle, this is also equal to 1 minus Tc over T hot. And this is extremely important, as we will see later on, okay? Thank you for your attention.